I think we can start. Thanks, everyone, for joining this new seminar from the Cambridge Ellis unit. Before going into the details, I want to thank our sponsors to the Cambridge Ellis unit for their support. And today we have Zeynep Akata as an invited speaker in our seminar series. Zeynep is a full professor of computer science at the University of Tübingen, and she completed her PhD at INRIA Rhône-Alpes and then worked as a postdoc at the Max Planck Institute for Informatics and then at the University of California, Berkeley. Before moving to Tübingen, she was an assistant professor at the University of Amsterdam, and she has received a Lise Meitner Award for excellent women in computer science from the Max Planck Society, a young scientist honored from the Werner von Siemens Ring Foundation, and she has been given also an ERC starting grant. Her research interests include multimodal learning and explainable AI, and today she's going to talk about the explainability in deep learning through communication. So I'm going to stop sharing, and I think, Zeynep, if you want to share your slides, you can do it now.
Okay, yes. Can you see it?
Yep.
Okay. Thank you. Thank you for the introduction and thank you for the invitation. It's really nice to be giving this talk. I didn't realize that this today is the first day of NeurIPS as well. So I didn't expect so much people to join actually, but it's very nice to see that there are those of you who have decided to listen to my talk. Okay, so the outline of my talk is as follows. I will first start with, in my view, how explanation and learning are related. I will talk a little bit about zero-shot learning. This may be already a very familiar topic for you, but maybe not everybody has thought about how zero-shot learning and explainability are related, actually. And then I will talk a bit about natural language explanations for visual classification decisions. So we can use language to do learning, but also we can generate natural language for the things that we have learned. And then again, briefly, I will talk about how we improve explainability of deep models using conversations, and I will finalize my talk with some final thoughts. Okay, so there is a very relevant quote from Einstein. He says in 1935, I think he said, "The supreme goal of all theory is to make irreducible basic elements as simple and as few as possible." So when we learn, we actually are trying to learn simple concepts and few of them, because we can't keep everything about the world in our memory, perhaps. And without having to surrender the adequate representation of a single datum of experience, which means we are trying to keep as much information as possible about the world while we are reducing it, that information into simple elements. And this quote has a lot to do with explainability, the way Tania Lombroso explains it in her cognitive science article, and it is very nicely illustrated in this example in her paper. She says, let's design this learning or the data sets for learning, where we are trying to distinguish between two different alien species. One of them is called glorps and the other one is called Drent. And we can see that they have different properties, like different shapes of the head and the body and different colors, color distributions maybe. And these all could contribute to what makes a glorp, for example. And the task is to learn these properties. Now, we might think that glorps are aliens with square head and square body, and we group them together. And we see that our classifier has made some mistakes. And in some cases, these mistakes might not be that important, but if what we have learned is wrong, then this is not going to generalize to a completely different or more examples of this data. So it's in some safety critical applications, it is important to learn the things, learn the distinguishing properties properly. And so we go back to the problem again. We investigate other aspects of the aliens, and we see that the shape of the feet is the important property in this case. So glorps are the aliens with pointy feet, and drans are the agents or aliens with flat feet. And if we have understood that this is the distinguishing property, then we make the correct classifier. So in summary, explanations are things that we are trying to generate. They are broad, simple, and contrastive. The broadness means they justify a broad range of observations or phenomena. And then they are simple, like the first quote that I was mentioning. They provide a concise description for the communication partner. This also depends on who the communication partner is, but we will come back to that later. And they need to be contrastive. So we need explanations to talk about why an object is classified to a certain class and why not to another class, for instance. And in computer vision, one tool we have that satisfies that criteria is the visual attributes. They are visually discriminative properties of objects that are that are simple, and some of these properties they are also annotated on a class basis. Some of these attributes are common for both of the classes, and if we are building a vectorial representation for those classes using attributes, then the vector will have the same value for that attribute position. And some of these attributes are specific to one class, then the vector of that class is going to have the values 1 and the other one 0. And some of these attributes are actually relative to each other. So we can also have values between 0 and 1. And this way of explaining the properties gives us flexibility, many flexibilities, but also it helps us keep much more information about the similarities between objects than just saying this is a one-hot encoding of the class and all the classes are equidistant to each other. And we can use these properties for building joint embedding spaces, like I show here. We could embed images in an image feature space, and this space could be fixed. It could be learned with, I don't know, ResNet or any other neural network. And then we embed classes in a class attribute space, and this space is also fixed. And this space encodes similarities between different classes. And now the task is to find the compatibility between these two spaces, such that images that come from the same class get embedded close to the attribute vector of that class and far away from the others. And if we have learned a good mapping, we can solve tasks like zero-shot learning, where during training we have access to some images from some classes, and at test time, we have images from completely different classes, and the model needs to be able to generalize to those other classes. So I see zero-shot learning as a downstream task for evaluating explanations. And there are many benchmark data sets out there for evaluating zero-shot learning accuracies. But two of the most frequently used ones are animals with attributes and Caltech birds data sets. The first one contains 50 classes. Usually 40 of them are used for training and 10 for test. And it comes with 85 attributes. The birds dataset is a fine-grained dataset with 200 classes of different types of bird species. And because the objects are visually very similar to each other, we need many more attributes to distinguish between them. So the zero-shot learning accuracy is measured by computing the number of correctly classified samples in a class, divided by the total number of classes and averaged in with the number of classes. We do that separately for seen and unseen classes, and then we take their harmonic mean. If we do this classification, or if we do the learning only with class labels, then the unseen class accuracy is 0, because there is no way the model can generalize to completely unseen labels. Learning with attributes gives us this accuracy. We see that the seen class accuracy drops quite a bit, and in the end, the harmonic mean is not that high actually. And of course, we need class annotated attributes for this. So the progress in the past few years in zero-shot learning tried to focus on these weaknesses. How can we keep the seen class accuracy the same? Improve both of the accuracies, the unseen class accuracy. How can we generalize to unseen classes, but also how can we eliminate the need for discretized expert annotated attributes? One way to eliminate the need for attributes is to use natural language. And for that, we have collected this data set. The images existed. These images come from the birds dataset that I mentioned before, and this is Oxford Flowers dataset. And we collected one sentence annotations for this for these images from a model Mechanical Turk. So there are no experts, field experts required. All we did was to ask the annotators to give us at least 10 words in a sentence and talk about 3 different properties at least, and then talk about only the object and not the background, and whatever they thought is interesting about that object. And then we can use these sentences to do zero-shot learning. The way I explained before, we could create this label embedding space and replace the attributes with that. And that gives quite good results already. Like if you go beyond 5 images per class, it is already as good accuracy as the attributes, and it is much less costly to obtain these sentences. But we could also use natural language as a conditioning variable in generative models, and we can generate data for the unseen classes. So in this work, this is now a few years old, but we were taking like a noise vector and then concatenating it with the sentence encoding, and then there is upsampling in the generator, and then the discriminator needs to say whether this image is real or fake, but also whether the image content fits with the content of the sentence. We can do this to generate images, and then we can add those images of unseen classes. We can add those images into the training set and then retrain the model as if we are training a normal multi-class classifier. But this doesn't give very good results. So with only real data, I was showing these results. With generated images, the results are not, in fact, the harmonic mean is even worse. So this is not better than having no images. So we thought, why not go why not use a model like that, the generative models? It could be anything really, GANs or VAEs, to generate image features instead of images. So this way, the model is not that heavy to optimize anymore, because, and also we don't have to go all the way from generating using sentences to generate image pixels and then extracting features from them, but we can directly generate image features from from the sentences, and that gives much better results, as it simplifies the problem much more. And now recently we have come back to that this problem again, and we thought, instead of assuming, like, given that very pre-trained large models have shown a lot of successes, some of these problems might be already solved, and but in fact, if we try to generalize to any kind of object that the model might encounter in the future, we see that being able to reuse the models that have been trained with different data sets and being able to adapt them to other classes is still an open problem. And of course, we can't assume the availability of class labels or images or image features even. This still needs a lot of annotation. So we are trying to go from instead of image features now, we are going from the classifier weights, from attributes or sentences to classifier weights directly. So we have this model that is a cross-aligned and a distribution-aligned VAE. There are two VAEs. One of them takes classifier weights and tries to reconstruct the classifier weights, and one of them takes attributes and tries to construct attributes. And they are optimized in such a way that the latent embeddings learned by the first VAE should be enough to reconstruct the attributes, and vice versa, the latent embeddings learned with the attributes should be enough to reconstruct the weights. This way, at test time, we can use this model that we had trained using the weights or the attributes of the seen classes to generate classifier weights of unseen classes. And if we have received an image that comes from a completely different class, one of those unseen classes, the model will be able to generalize to that. And that gives much better results in this problem, in this task. As a conclusion for the first part, attribute-based and natural language explanations provide an intuitive interface for the model, and they provide side information to learn representations that are strong without having to surrender the information required. And these additional information complements visual information in the limited data regimes. I talked about zero-shot learning specifically. So now I want to talk about how we generate these natural language explanations. And before I do that, I want to explain, in my view, what is the difference between a description and explanation and a definition. So in terms of image relevance and in terms of class relevance. With one example, what a description looks like is if we have these two images that come from two different classes, but the birds are behaving in a similar way. They are both in the water, and they have both similar color distributions. The descriptions may look quite similar. They both talk about a large bird with white neck and black back in the water. So in this sense, in terms of descriptions, these are not very distinguishable. In terms of definition, they are very class relevant. So the definitions will talk about class specific properties, and they may talk about things that ask the properties that may not be visible in the image. It is not image relevant, basically. So may talk about the legs in these examples. The visual explanation, on the other hand, is like a combination of the two. It needs to be image relevant and also class relevant. In this case, the visual explanation needs to talk about the red eyes, for example. This is one of the most important properties for this object. And the bird being in the water doesn't really matter in this case. Yeah. So now we are trying to generate explanations, and we use this kind of a communication game for it. The user may have partial observation about the environment, or just may be not knowledgeable about the species, so asks what type of bird is this, and the model says it's a cardinal. This is directly the prediction. It may be correct, but we don't know whether it is or not, or we don't know what is the evidence for it. So the model needs to expand that prediction to saying, because it's a red bird with a red beak and a black face. And so how we generate this kind of a sentence is we take a deep fine-grained classifier. In a way, this is the decision maker is a black box. It gives us the image feature and the predicted category, the class prediction, that we concatenate and that we feed to a language model. And this language model is trained with two losses. One of them ensures the fluency of the sentence, and the other one ensures the class specificity of the sentence. So here we have a sentence classifier. After the sentence is generated, we try to classify it to the correct class, because it needs to be class specific. It needs to contain all the information about that class. If the sentence has enough information to be classified correctly, then we have a high reward. We keep the sentence, otherwise we sample a new sentence. So some results, some interesting results. This data set contains very fine-grained species of birds, but also the male and the female species might look very different, and they are included in the same category, of course. So here the male bird has a red spot on the neck, and the classifier picks up on it. The description talks about the red. The generated description talks about the red spot, even if it is not present. But the explanation model doesn't talk about it when it is not present. There are some interesting failure cases. So these two images belong to the same class. Actually, this image was misclassified to cactus wren. This object looks quite different from this one because it's a juvenile bird, although it contains all the class-specific properties like the shape of the beak. The color of the feathers look very different, so it got classified wrong, so a wrong class, and the explanation talks about the class-specific properties of this class that are visible in this image. So coming back to the previous example, so far our method is able to generate sentences that give a justification about a classification decision, a post hoc justification, but so far there is no feedback loop that ensures the user that the evidence is actually in the image, or to evaluate whether the model is taking correct decisions. So we want to implement that feedback loop where every noun phrase that gets mentioned in the sentence need to be grounded on the image. there needs to be a bounding box that surrounds the property, and that should match the noun phrase in the sentence. And then I mentioned that ideally an explanation needs to be contrastive. So the user might wonder why not a Vermilion flycatcher, and the model needs to think about how a Vermilion flycatcher looks like, what are the class-specific properties of that object that is not visible in the original image, and say it's not a Vermilion flycatcher because it doesn't have black wings in this example. So we can take the same explanation sampler as before that had a deep decision maker that gives us the image feature and the class label and the language model that generates the sentence. Now we can take the sentence, divide it into noun phrases. It's a part of speech tagger, so no learning involved here. And then we use an explanation grounder that was trained on a different task, because in this data set we don't have bounding boxes, but we apply it to this data set. And this explanation grounder gives us the matching score between the noun phrase and the bounding box. And we can do it for multiple sentences and then rank the sentences based on the cumulative score of the sentence that measures the correspondence between the bounding boxes and the noun phrases for all the noun phrases in the sentence, and say the first sentence is the most relevant to the image, so we keep that. We see that doing this forces the model to forcing the model to talk about visible properties in the image, and also forces the model to talk about more class-specific properties. So the model does better in the original task as well. And then coming back to contrastive explanations, we generate the first sentence. This bird is a crested auklet for this query image because of certain properties. And it is not a red-faced cormorant. This is the class of this image that is the closest in terms of visual similarities to the original image, to the query image, that belongs to another class. That's how we decide on the counterfactual class. And then we look for the properties that this class, the class of this image contains that have a very low score when we try to project it onto the query image. So the long flat bill property seems to appear for the images of this class, and they give a very low score when we try to project it onto this image because it doesn't have long flat bill. This is how we generate the counterfactual sentence. So it's a bit of manual processing. So there are many different ways to do the grounding, the visual grounding. And as many of you may know, these many attention-based, attribution-based methods have come up in the recent years, where they use they try to basically point to the evidence for the classification decision. But in most cases, these attention values are presented in relative scales, and it is not very clear what these values mean. So when we, for example, show the CAM attribution for class A, could be any, like one class for this image, it shows the entire extent, or it highlights the entire extent of the bird. And for another class, maybe different properties are highlighted, but still the attention map covers the entire object. But if we show these two examples, these two results to the user, it might not be very clear why this image is classified to class A and not class B in the end. So in this work, we were trying to calibrate the attention values such that, and also make them kind of more focus on the properties, the attributes that I talked about that are important for the classification decision. So in a way, combining the aims of the previous paper with another visualization technique. And when we do that, then like with this calibrated uncertainty values, it's the differences between these classes seem to be more easier to understand. And so taking this idea one step further, we can actually use the information that is contained in this attention maps to truly form a feedback loop to the decision maker. So if, let's say, our task is now to answer the question of whether if you should hug this animal for this object, the VQA model has already made a decision of yes or no, and then the attribution map shows this is the evidence for the decision. We could use this attribution map to inform the VQA model, and also to use it in another pre-trained language model to be able to generate the language-based explanation. So typically, VQA models gives the class decision the answer of the question, but they don't go beyond that to generate an explanation. So we can use a pre-trained language model that was trained to generate a caption, and we can basically use the answer of the VQA model and together with the attention map to generate the explanation. The explanation says no because it's a bear, and this explanation needs to be grounded in the image in the way I described before. Okay, as a conclusion of this part, via explanations via natural language are an effective means to justify a decision to the user. Of course, it depends on who the user is. In this work, we were assuming that the user is an end user who is not interested in learning the inner thought process of the model, but just is able to evaluate the consistencies and inconsistencies of the model's decision. And the model's decision needs to be, the explanation needs to be class specific and as well as image relevant in this case. And it needs to point to the evidence. It needs to be contrastive and also model uncertainty when we talk about the class attributions. So how would we use conversations to improve the explainability of deep models? There are many different ways. Also, in this work, we were interested in trying to open up the black box a little bit, and using language as a constraining mechanism for the decision maker. And as a byproduct, we get a decision tree, basically, and we use attributes as a tool for it. So the setup is that two models are communicating with each other using attributes as language. And the first model has access to, or has a set of predictions, has decided that the object that they are looking at might belong to one of these four classes, but not sure which one. So they need to come up with a question that eliminates some of these classes. And the other method has access to the image, and it can predict anything about the image, but it is not allowed to say everything and only answer the question. This is how this decision maker is constrained. the answer to this question for this image is yes. That constrains, that eliminates two of the classes, and then the remaining two classes provide information for the next the next question. Does it have whiskers? No. This eliminates one of the last class, and the first model can come to the conclusion that it's a dog. So we have two agents communicating with each other. The first one is called recurrent decision tree agent. It has an LSTM model, a language model, or a sequence-to-sequence model with an extended memory mechanism that keeps track of the previous answers to the questions and decides on the next question. So we take the hidden unit activations of the LSTM in this case, and we do an attribute prediction. And the attribute with the highest score determines the next question. And that question is communicated to the next agent that has access to the image, can process the image, and decide on which attributes are present in the image. But it is not allowed to communicate back all of the answers. It communicates back the answer of the question that it was asked. And that, in this case, it determines the end of the game. And the class prediction has been made. This way of decision making could be useful for tasks like this. We have two images that may belong to the same class, and we can see based on which questions these images get classified to which class. Both of the images have classified to have white underparts, so they fall into the same bucket. And then over time, they get separated into two buckets based on the black wings property. This is actually, in this case, wrong to classify this image as a different class, but the image doesn't contain the black wings property, so we can understand where the mistake is coming from. So it is still useful to be able to see where the model is making a mistake in this case. And I mentioned that the male and female birds may look quite different, and that may influence the properties that the model learns to distinguish between different classes. And in this case, the wrong property that was learned was black crown. Only the male birds in this class contains black crowns, black heads, and the female bird, that's why it was classified into the wrong class. I mentioned in the beginning that the understanding of the communication partner is important when we build the language of communication. And here in this work, we were exploring that. So we have designed a game, an image reference game, where two agents play with each other. The first agent looks at both of the images, picks one of the images, and describes it to the second one. And the second one needs to pick the same image. But the second one doesn't, it doesn't understand some of the properties, because in this case, it's colorblind. And all the color-related properties will either lead the second agent to pick either the correct class or the incorrect class uniformly randomly. And this could provide a learning signal to the first agent. By playing this game together with each other many times, the first agent learns that the second one is not able to understand colors. So although the color might be the most discriminative property, the first one learns to not mention it, basically. It's a two model communication game. Again, we have a speaker and a listener. Actually, both of them have the same perception model. The image feature gets extracted, and we predict attributes in both cases in the same way. And then we contrast these attributes, and the speaker decides which attribute gives the most information to describe that image to the communication partner. In the beginning, the color-related properties, when they are the most discriminative property, they get communicated to the second agent. And the second agent is colorblind, which means the predictions of the color-related properties have some noise. And as a consequence, whenever color-related property is queried, the reward is -1, and that gets communicated back to the speaker, and the speaker updates its own mental model about the communication partner, its agent embedding. And over time, the speaker learns that in this case, the color properties are not very informative, so it picks the shape-related property and gets a positive reward. Some examples. In the first game, for all of these cases, the most discriminative property is color-related, and the chosen property is color-related. The communication partner is colorblind, so the answers are wrong. Over time, the speaker agent learns to update its belief and talk about shape-related or patterns-related properties. And then in game 100, it has converged. Although in all of the cases, the property that is the most informative is color property, the chosen property is always shape-related, and that leads to the correct response. So natural language is a natural means for communication, but if we don't have access to it, we can still create a language that would find simple primitives that are contrastive, that satisfy the conditions of being an explanation, in my view. And in this project, we were trying to do that. So different people can draw the same object in many different ways. And when we look at this object, we can recognize that this object is a face. But it is very difficult for a neural network to come to the same realization, and this is because they may lack the compositional understanding of the world, and maybe the abstraction that is required for it. So we feed a model with a language that we have designed. The language is composed of these primitive shapes, and the task is to represent the input shapes in terms of these shapes, basically the shapes of the language. And then we can do, once we have done that, once we have created this simple representation, we can also do further abstractions to see when does an object stop being that object, basically. And this could be evaluated using a communication game, like a Pictionary style game. The first agent starts drawing the primitives one after the other, and the second agent is trying to guess what that object might be. And once all the primitives that are necessary are drawn, then the communication concludes. The second agent is able to guess what that object is, and more primitives than that is not necessary for the communication. We conclude that. We could extend the same idea to 3D. We might have multi-view images that are taken, like those are 2D images taken through a cell phone, maybe. And then there are many different tools out there that reliably segment these images. We have image segmentations. And then the task is to take these binary images and use them to create a 3D or reconstruct this object in 3D. And for that, we have different primitives that we can combine together, that we can compose to build the object. And one application for it could be mixed reality application. For example, there is a robot walking around trying to tidy the room or something, and to decide on which part of the object to pick from. This could be an interesting application for it. So communication with the user can constrain the system for improved interpretability. I talked about these decision trees based model to showcase that. Communicating with the user is an effective means for evaluating the conceptual understanding of the model. We need to understand, or maybe it is very obvious to us that the communication partner might have a different understanding of the world, or restricted understanding of the world. For example, if we talk to a 5-year-old versus a university student, we always choose different words to express the same concept. And in another work that I presented, we were aiming for the same functionality in a simplified scenario. And this can be done while learning simple primitive representations of the objects. So in case we don't have access to language, we can build our own like simple representation of the object. In summary, I talked about learning with basic, simple, and contrastive elements of understanding is important. I talked about explanations via attributes and natural language. I showed that zero-shot learning could be one downstream task for evaluating explanations, because the explanation needs to contain all the properties, the discriminative properties of the class. And vision is complementary for generating natural language explanations. So in the second part, we talked about how to generate these explanations. And in the third part, I talked about how understanding the mental model of the user is necessary for effective communication. Also, we can use explanations as a means for constraining the decision-making process of the decision maker. This opens up the black box a little bit. I gave some talks recently in different contexts, and that made me think about in which applications of that are relevant to the society this kind of explanations would be useful. And there are many scenarios, of course. One of them is for Earth observation. I have learned that they look at, they try to determine based on satellite images whether to, I don't know, in this example, should we build an apartment here? Could be one question that the user might ask. And we expect the model not only to say no, or not even to say no, there are so many car parks and roads, but also point to why this explanation has been generated. And the user has the right to question the explanation, going one step further to what I discussed before. And the user might ask, what does this mean? And we would expect then the model to elaborate on the explanation and say there are not enough green spaces, water sources might be limited. This is of course one example, and it may require very specific data annotation, but it has been shown in many studies that if the explanation is so gives more and more information about the image, about the data that we are looking at, that model is much more trustable by the user. Another safety critical application could be health communication. This we encounter in our everyday lives. The user might ask, am I healthy, looking at a scan or something, and the model needs to say, looking at these parts of the image, I have decided that there is a possibility that this may indicate diabetes. And then the user might ask again, what does this mean? And now the model needs to elaborate on the uncertainties, the meanings of uncertainties, and say 30% of the patients for whom this diagnosis was made had diabetes. I think with all the progress that has happened recently, some of these tasks are already solvable, but some of them, the ones related to compositionality or further elaboration of context-specific information is still far from reach. And yeah, so these are my final thoughts about what is the use case of all of this research. And that's the end of my talk, actually. I would like to thank you for your attention. And if we have some minutes, I would be happy to take.
Yeah, we can. Yeah, thanks. Thanks a lot for the interesting talk. We still have some minutes for some questions. I want to ask anyone who is interested in asking anything, just write something on the chat. And meanwhile, I'm going to ask one question. I mean, you have presented very interesting results. And my question is about whether this type of techniques, they could be applied in other domains different. Obviously, there is a lot of, I mean, my main point is about images. It's very easy for humans to look at images and kind of interpret images. And maybe if you have an explanation, it's quite easy to see if the explanation is fitting the image or not. Yeah. My question is about, could you apply similar techniques in other domains, maybe where the data is not going to be images? For example, I'm thinking more about, for example, like tabular data sets. Yes. Where explanations might be like more complicated. What could be like done in that setting, for example? Or could you say a few words in that case?
Yes. So all the learning signals that feed the language model in our case comes from the vision model. But the sequence-to-sequence models that actually generate the explanation could take signals from any other model. They are completely they are not completely disjoint, but I think if there is enough signal for the explanation, and there is a ground truth explanation, or ground truth, at least ground truth descriptions of the data, then I can think of this as extendable to other domains. I can't tell you any evidence that we have done because we haven't looked at other data types. But I'm interested in looking into other, like, for example, for drug discovery, this could be important. For law applications, this could be important. Maybe you were also referring to that. Yeah.
I mean, I was thinking about also some work that was done some time ago by some students of CUB here in Cambridge. They had this paper on the automated statistician, and you would basically get like a data set, and they would feed like a predictive model, and then they will be able to tell you about properties of this model. They would say, oh, maybe your data has this particular temporal pattern, and it was just generating like a kind of some description of the data in the format of like a scientific paper. But obviously, I mean, that was like quite different from the methodology, and the approach was very different from what you have been describing. I was thinking of doing something similar in the sense of tabular data like that, for example.
Yeah, I see. Yeah, very interesting.
Cool. Do we have any questions? Anyone feel free to ask any questions. You can also write them in the chat if that's the case. Okay, we have one question. Have you compared the performance of transformers versus older language models? I would guess for these really specific tasks, older models work just as fine.
Yes. So of course, the more recent works use transformers and not LSTMs. The one that I was talking about this, should you hug the animal? This work uses transformers, and we compare with the results of LSTMs there, and the results are much better with transformers. But then again, this wasn't a very fine-grained classification problem. We were working with visual question answering type of explanations. So it's interesting. Indeed, maybe simple models could work with specific data like this. Yeah, we should look into that. Usually one somebody started this research and somebody else has continued, and the trends have changed. So nobody thought of looking into the previous works, of course, at least in my group.
We have time for one more question. There is one in the chat. It says, years ago, I was in a seminar where we imagined creating explanations in decision-making, summarizing preferences of multiple experts, their consistency and inconsistency they are learning. I wondered if you might be interested in generating this kind of explanations. I can imagine that the focus is on these multiple experts, for example.
Yes, actually, this is very interesting. I was thinking also about this. What happens if the experts, the decision makers don't agree? Like there are multiple decision makers and they don't agree, or there may be multiple explanation generators that don't agree. Then which decision and which explanation should we give to the user? And in this kind of scenarios, maybe I don't know, majority vote of different experts could be done, or early in the decision-making process, some of the disagreeing experts could be eliminated. This could be an interesting thing to look at as well.
Mm-hmm. Good. Sorry, we're out of time. Thanks a lot for joining us in this seminar, and yeah, hopefully we'll see you in person.
Yes, hopefully in the future at a conference, probably. Thank you very much.
Thanks, everyone. Bye.